Hi, everyone. My name is Matthew Lawhon. Thanks for coming. It's an honor to present PinFM, the Pinterest Foundation Model for User Activity Sequences at Billion-Scale Visual Discovery Platform paper. First, we'll talk about the background for this talk. The motivation for this paper comes from past innovation in ranking models. This includes Pinterformer, predicting user interest evolution from years-long user sequence data, Transact, which brings real-time transformer-based sequence processing to online models, and large ID embeddings, which memorize every single image signature for 20 billion parameters. A natural question is, how can we unify all of these techniques? So the goal here would be to achieve a step function upgrade in user sequence understanding, where we're able to train with 2 years of user sequence training data. We're able to serve with real-time sequences and real-time sequence processing. We have a 20 billion size parameter model. And the goal is to avoid significant training and serving cost increase given real-world industry constraints. Our solution here is to adopt a pre-training fine-tuning paradigm. Specifically, we pre-train our foundation ranking model with 2 years worth of long sequence data, such that the pre-training cost is amortized per surface because it's shared across many downstream use cases. And this model is then brought into online surface models like our home feed ranking model and is fine-tuned in the same way that those models are trained before. Later in the talk, we'll cover how we're able to afford real-time serving for such a large user sequence model component. Next, I'll elaborate on our methodology for pre-training and fine-tuning. So the pre-training task is a purely sequential task. We focus on next pin prediction, and specifically, we use an info NCE-based contrastive task to predict whether future items are positives on the basis of previous transformer outputs. The way that we select the position of those outputs and the position of future items differs, and we use 3 specific methodologies. We use the next token in the sequence, we use an arbitrary future token in the sequence, and then we have a special component of the sequence which isn't actually processed by the transformer at all and is purely used for long-range future token loss. When we fine-tune this component of the model, we now have a notion of a user sequence and a candidate pin. And what we find works best is we insert the candidate pin into the sequence and then use the foundation model to extract embeddings for this candidate pin and feed those into the downstream surface model. The foundation ranking model is then fine-tuned via a combination of the same loss that is used in pre-training and the binary cross-entropy loss that is used to train the ranking model. Next, we'll talk about some of the efficiency considerations. So one of the key issues with this technique is maintaining reasonable cost. And the key insight that drove the optimization for this paper is that we're normally ranking multiple pins for the same user at the same time. Specifically, in training, this user to pin ratio might be 1 to 10. In serving, this might be 1 to 1,000. So the natural question is, can we deduplicate the work that we do on understanding user history? And the answer is yes. The way that we do this is through the deduplicated cross-attention transformer component. You can see the paper for a more rigorous treatment of this. But it's largely shown in the diagram here, where instead of processing the user sequence and the candidate pin for each candidate pin, first we process the user sequence for each unique user sequence, We save that KV cache and broadcast that to the candidate level. And then we perform cross-attention with only the candidate pin in the query sequence, which allows us to see a 600% serving throughput increase and a 200% training throughput increase as a result of deduplicating most of the user level compute. Lastly, I'll touch on a case study of productionization, which focuses on how we handled the cold start problem. As you might expect, integrating this without any sort of tricks into our ranking model was helpful for overall content, but was extremely harmful for the freshest content. In this case, we're looking at pins that are just 7 days old or less. The intuition here is that fresh pins have unreliable ID embeddings, and so as we're teaching our home feed ranking model to increasingly rely on them, it's going to get far worse at predicting those engagements. But we found a few tricks to be very helpful. First, we wanted to give the model the ability to rank pins that don't really have useful IDs, and we achieved this by adding a small amount of noise to the IDs. Next, we also wanted the model to explicitly rely less on ID-based features for fresh pins. To accomplish this, we added a pin age-dependent dropout, which applies a higher dropout rate for fresh pins. And lastly, we altered the construction of our candidate level sequence in two ways. We added an unconditional BERT-style class token, which allows the model to learn purely user-level information, which intuitively may be more important for low-signal pins. And then additionally, we stabilized the candidate pin token by adding the GraphSage embedding. So to summarize, we were able to achieve our step function increase in user sequence understanding. We surmounted the challenge of training with 2-year data by adopting a pre-training fine-tuning paradigm. We were able to serve in real time by using request level serving and the deduplicated cross-attention transformer. And lastly, we maintained compatibility with existing ranking models by simply fine-tuning this new foundation model component with the existing ranking models. Thank you.
Do you retrain foundation model as user sequences could change?
Yeah, good question. So definitely something we ablated was the importance of freshness in the pre-training job. And yeah, we currently retrain it every week, but we're sort of like continually monitoring, and this is an area for active exploration, the sensitivity to freshness.
Okay, thank you. And the second one is, when using next pin prediction, are you incorporating the existing recommendation system biases into the foundation model?
Yeah, I suppose so.
Thank you.
Thanks for the presentation. Have you analyzed the output of the recommendations in terms of novelty for the pins? Because it seems like the model is biased toward more popular rather than recent items while training.
Yeah, that's definitely true. Sorry, I may be misunderstanding the question, but I think that that's largely handled by the sort of like fresh pin specific treatments we discussed at the end. Sorry, did I answer the question?
So the question is like if I understood that correctly, we reduced the amount of information brought by the fresh pins while training to reduce the noise in some sense.
Yeah.
And this might affect the results, so the results will contain less fresh items in the output. Is it so, or like you don't know yet?
No, I wouldn't say that's the case. I think the main impact of the sort of like fresh pin specific treatments is we actually saw an increase in the distribution of that kind of content when we sort of like added some of this domain knowledge into the model, that like this component of the model is like not really trustworthy for that kind of content segment. When we did that, the model was able to better rank those pins, and we increased their distribution.
I'm curious how long it takes to train the foundation model.
Which part?
I don't know. Feel free to choose.
Pre-training between 1 and 10 days, depends on how many GPUs you use.